take it away.
Good evening, everyone. Welcome to 3DQ's live stream. This is live stream number 7 for us. We're pretty excited tonight. Of course, we have me, Steph Sharp, CEO of 3DQ Systems, and Mateo, my co-founder and also Chief of Innovations, as well as Stephen McCulloch, who has done a lot of our hardware innovation and also recently a bunch of material testing. So we're really excited to hear from him about what materials are working with the Quinly bed. And as a very special guest tonight, we have Professor Eric Wooldridge from Kentucky, which is amazing. We love working with our American counterparts. And he actually runs the Additive Manufacturing Center of Excellence down in Kentucky. And he can tell you a lot more about that than I can. So, first, I just want to let people know, for those of you who are new to the live stream, because I know we have a number of new people tonight, the live stream is a very informal forum. This isn't scripted, so you're free to jump into the chat. On Twitch TV, you can simply sign up and jump into the chat, ask us questions, and we will answer them on the live stream as much as we can. You can ask me, you can ask Mateo, you can ask Stephen, or you can ask Eric. And I think it would help just a little bit to get started, Mateo, for you to just tell people a little bit about Quinly, and then we'll jump into talking to our guests.
Sure. So material testing on an Ender 3, which is what we're going to go over tonight, it's not just on any regular Ender 3. We'll be discussing all the mods that we got, these pretty exciting kind of high temp flexibles and just weird exotic materials working on there. And something special about our Ender 3 is that we're running the Quinly kit, and a major part of that kit, which is that it automates your printer. So not only can you print parts in these crazy materials on a very inexpensive printer, but you can actually have the printer run unattended overnight, printing dozens of parts in these like super cool, pretty much what would be considered engineering materials. Where you'd normally need like $1,000 printers to print. So it's some pretty exciting news. And of course, the key to that is the main component of Quinly, which is the automatic release bed, the VAAPR bed, as we call it. And so we'll be talking about, well, Stephen will be talking about how he got all of these materials working on that bed, and hopefully that kind of inspires you guys to start looking beyond PLA and ABS for some of your projects. We'll also be talking with Eric Wooldridge about his pretty extensive industry experience as we go through all these materials. So hopefully that also kind of inspires some ideas of if you're running this micro factory with these crazy materials, you could potentially look into doing parts for certain types of industries. So I'm super excited about that.
Yeah. So I think what we'd love to do is start off with Eric. If you could tell the folks a little bit about yourself and the Center of Excellence and all the interesting work you've been doing with the FDM type 3D printing. That'd be a great way for people to get to know a little bit about you and the center and what Kentucky is doing, which is very leading edge in additive manufacturing.
Okay, well, I'm glad to do that. Thanks for having me tonight. So at the end of the day, you could easily say what we're doing is we're trying to get additive manufacturing mindset and skills into the workforce of both Kentucky and the U.S. as quickly as possible. Our end game is to create a workforce of individuals that understand how to 3D print and move away from the keychains and trinkets to advanced applications using generative, using high-strength materials, and using it to make things that actually matter, things that they can sell, new businesses that can be started up, even just solving problems that occur in the manufacturing industry. And we saw with COVID what happens to a fragile supply chain when something, something like a global pandemic happens. And we've also seen that in terms of natural disasters. And additive manufacturing is the first technology to ever be present in one of these situations that can step in and fill that supply chain gap. And so we've seen that folks realize this, and the missing link is just not enough people doing it. So what we're doing is taking the skills around this technology, packaging them up and getting them to students, and also giving them to teachers and moving them, pushing that needle further. We do a lot of low-cost additive manufacturing applications because that's the easiest way to train folks. But the things that we're making are cutting-edge products. We often refer to it as next-generation products, products that are lighter, faster, stronger. And that's our goal. And we know that if we build this skill mentality into our folks as they go get jobs in the medical field, in the manufacturing field, in just transportation, and even the food industry, they will go into a job and see a new opportunity for additive and bring that mindset to that job and then create innovation. We also love it when companies realize they don't have to put in a $10,000 investment to have a single prototype made. When they plan for additive, they can turn around and take their idea and go straight to market with a simple 3D printer. We also love to empower folks with a business model that is get a printer, get the understanding, and take that printer to make it produce for you and then sell it on Facebook, sell it on Amazon. And we have a whole platform of marketing capability. So it's a lot of things at once, to say the least, but it's all around the fact that 3D printing is not so much about the printer, it's more about the mindset and then the ability to use the printer just to create this next generation product or an idea that you've had that you've never taken the time to actually dive into or in the investment for. So that's in a sense as the grand scheme. We do a lot of the high-end stuff, but we do a whole lot of FDM applications at the college and across the state.
Yeah, and it's very exciting. I know we're going to talk more in detail about some of the things you've done. And interesting, too, that you mentioned the economics, because the last couple of streams we've actually been talking to people who have been 3D printing and selling their parts on Etsy, some for gamers, some for holidays. Next week, we're going to be talking to some folks from the UK about what they're printing in terms of models and props and cosplay type of printing. So lots and lots of applications, as you say. So just to give people a bit of an overview again about today, we have been doing material testing very rigorously in the last few weeks particularly. We've been producing parts for the last couple of years, but Stephen's been doing some very significant material testing. And Stephen, do you want to talk a little bit about kind of the range of materials you've been testing recently?
Yeah, for sure. So over the past year or so, we've really just been printing PLA, a little bit of ABS, but that means we haven't really tested the full capabilities of our system. And these build plates are really good for PLA, they're really good for ABS, and up until now, we didn't really know how well it worked with the higher performance materials and things like polycarbonate, nylon, and also the flexibles, and even just some standard materials that we just didn't really have a good reason to print, such as PETG. So over the past couple of weeks, I've just been going through our stock of filament, all the samples that we've been getting, and just all the spools that we had for odd jobs, and I've just been trying to get them to print on our build surface, and yeah, there's some interesting results.
Yeah, I think one of the most exciting things about these results, and it ties into what Eric's been saying, is that giving a printer under $1,000 the capability to run these engineering materials without having to do too much modifications. The modifications on our Ender 3s, which is like a $200 printer, they add up to about, I think in total the printers are still under about $700 US.
Yeah.
With all the mods, and now you've been printing from PLA to polycarbonate. I think that's really impressive, and I also think it really giving people the accessibility to these materials could spawn a whole host of new product innovation.
Yeah, yeah, like having the right material for the right job is very important. It's just as almost as important as like proper design, I think.
So interested to know, Eric, what materials have you tested with the FDM style printing? What's the kind of the range that, because I know you have a lot of access to things we don't have access to. So I think our listeners would be very interested in that.
We have we've printed with just about everything from your good old fashioned PLA all the way to beer, and hops and hemp and seaweed and carbon fiber this and nanotube that and infused metals, obviously nylons, polycarbonates, PEI. You know, we've done them all, and because at the end of the day, and I attribute this movement to the smartphone and app combination. Now that we have this technology, such as the Enders and all the FDMs out there, we've got this smartphone, so to speak. And now the material apps are just flooding in. In fact, we see new materials released almost on a monthly, sometimes weekly basis.
Yeah.
Yeah,
And
definitely what we're
it's
finding.
crazy awesome.
Yeah.
Yeah, I mean, we right now in the lab, the other lab, we have a material we have a mask concept being printed off that's in an antiviral filament, you know, an antibiotic filament, conductive filament. I mean, we can print in marble. So it is limitless in terms of materials, and it's only going to get better.
Yeah.
Shape change, responsive to electricity, it's all going to be possible.
Yeah, I think one of my biggest takeaways from Formnext last year was I spoke to a whole bunch of like material development companies, and something I found really exciting was that their new materials, they weren't even developing an injection molding alternative to them. Like especially a lot of the like the compostable materials or biocompatible materials, they were developing them solely for 3D printing. I found that really fascinating because I think that is an indication of where the industry is going to go into the future. Clearly, they see 3D printing as the main kind of manufacturing process for some of these products.
Yeah.
I always point out is that you always need to follow the money. And so we started making a point to track where all the big investments go. And when you start seeing the biggest chemical company in the world, BASF, and then the top five, DuPont and everything else, when they start spending millions of dollars to buy up companies and then start producing their own resins and filaments for 3D printers, that's a sign to so many industries. And the fact is that some of these materials we can print with, you can't injection mold. We did a project with a company from the Midwest, and their industry was basically the oil fracking industry. And they had a material that was ideal for this. They had a material that was actually very sustainable in concept, and they could not injection mold it. They had the guy literally had to come up and spend a weekend with me so I could show him how to print with this material they had, so that they could actually make the product they wanted. So a lot of this cutting edge stuff, this exotic materials that we can do something with, you can injection mold with. So it means it's pretty much being left on the table. If you're only considering conventional manufacturing, you're just basically not getting to take advantage of it.
Absolutely. So before we dive in to all these materials, somebody was asking, he was wondering how we were doing the high temp on the Enders. We'll actually go into all the mods that we've done, and I know you guys, part of your work is teaching people how to mod their own printers. So we'll be going into kind of the different mods that either we recommend for the Ender or that we had to do specifically for these materials. We'll go through the list on the left side of the screen there, pretty much one by one. So before we jump in, you are actually one of the reviewers for the Quinly kit, so it might be interesting to know what kind of drew you to our technology around the automation specifically.
Sure, and that's an easy one. I mean, it's automated. That's plain and simple. During COVID, and I was telling you all the story earlier. During COVID, we had educational facilities shut down, and yet had a supply chain collapse of PPE, personal protection equipment. And so literally we had to fire up our banks of printers and produce thousands of face shields and PPE. And the problem was somebody had to be there in the middle of the night to hit the button and reset all those printers. And that someone was me. So essentially, at night, I'd have to, sleep in my office and get up and do that. And I'm thinking, especially now, because we talked about it, I was like, this has been out last year, I'd have got a lot more sleep.
Yeah, I know, damn it.
I think that's our new tagline,
yeah.
Eric. If this had been out last year, you'd have got a lot more sleep.
Yeah, what's that saying about hindsight?
It's 2020.
It's been great. Adhesion's always the problem in this process. And so the simple solution that you all have provided by just basically having a material that grabs and holds and then completely releases, and you can actually just use your extruder to knock it off. I mean, it's simple, it's elegant, and it solves the problem. And that would have been, because we used a ton of enders to produce a ton of face shields, and we had other ones too, bruises and artilleries and everything else going. But I could have fired up and converted over all of my enders in a quick period of time and had them just producing days on end without having to monitor them. That would have been great.
Yeah, and that's literally what we did in our 1,000-hour test. We did 5 days straight, 9 printers, 1,000 hours, and they just went. And I think I was saying to you on the pre-show that it was 0.3% of the time was an operator present. And what was he doing? Changing filament. We should have gone for 2 kilo spools. And
that's right.
a little bit of
bro, you can use. That thing's monstrous. We used a couple of those, but we still had to turn it on.
Yeah. Well, you combine those two and you got a huge solution.
So why don't we go through and see what the vapor bed that comes with the automation kit, what it actually enables you to do. I think we're kind of starting with personally my favorite material that we've tested so far, which is polycarbonate. So Stephen, why don't you talk about a bit about how you were kind of printing polycarbonate, how you found that you got it working on the ender with the Quinly upgrade.
Yeah. So polycarbonate's like a pretty high temperature material, and it needs a high temperature mainly because like one of its main properties is that it has a high glass transition temperature, and that means it holds its shape up until about 110 degrees Celsius. Which is a lot better than, for example, PLA, which is around 60. Mm-hmm. And so when the glass transition temperature is up at 110 degrees Celsius, the Ender 3 beds are also just about as powerful to get to 110. And ideally, we push that a little bit higher just so that the part adheres properly. Mm-hmm. So, we know that our build plates work best when we print these materials on a hot bed, and the bed has to be hot enough. So for the Ender 3, what we had to do is figure out how to get the bed hotter than 110 degrees so we could print polycarbonate. So there's a very simple upgrade that I did. It cost about $20 total for a couple rolls of tape and some foam. And it was essentially just a layer of insulation underneath the heat bed. And it was super simple. It took me about half an hour to do. I took the bed off, applied some tape, applied some foil tape over top of that. I think Mateo's getting a picture up on the screen right now.
Yeah.
And this allowed me to go from a max temperature of 110 degrees on the bed to 140 degrees on the bed. And so these polycarbonate parts I have here, this is a filament dehydrator extender. These were all printed at 135 degrees on the Ender 3 bed using our vapor build plates.
And so what is really fascinating about getting polycarbonate to print on an ender is that an ender is a completely open printer, right?
Yeah.
Heat loss and the heat gradient from a really hot bed to a really cold ambient temperature is like a major driver of warping. So did you find that warping was an issue with these?
With polycarbonate, warping is a little bit of an issue. I found like a few things that you can do to improve warping is simply just crank the bed up, because I think it warms the air around the part a little bit, and that helps, I guess, smooth the gradient out a little bit. Also, of course, first layers are important. I print the first layer less than 10 millimeters per second, super slow, super thick, super hot. I mean, we're using an all metal hot end. I think people are talking about that in the chat. Yeah, the
Yeah.
all metal hot end is very necessary.
It's what you need to actually print it onto the vapor bed, but the vapor bed can handle those temperatures, right?
Yeah, so yeah, the vapor bed can totally handle. I think I was printing 285 for the first layer on these. Um, and yeah, the polycarbonate stuck down really well during printing, and it released very nicely actually. While it cools down, you can actually hear the part cracking and kind of falling off the bed even a little bit. At about 60 degrees Celsius, it just completely detaches. And you can see a picture here of me just wafting a piece of paper and everything just falls right off.
It's got enough adhesion to hold down a thin walled part that covers the whole bed, but it can also release it, is what you found.
With a piece of paper. So one of the things that we want to make sure the viewers understand, Eric, because we get a lot of confusion around this, is people say, oh, you're jamming the part off with your, with your nozzle and you're going to break your machine. And we're saying, no, we're nudging it off. It's like, it's, there's not a lot.
Breaking. We've run that enough to know it's sometimes it'll just about slide off on its own. A nice good breeze or something comes to the room, it's gone. So which really impressed us. Yeah. Yeah. Sorry.
Yeah, for those in chat, because someone was asking, it's the bed itself that comes with this kit. The automation is in that when it's hot, stuff sticks really, really well, and when it's cold, stuff completely releases. So you eliminate the need for scraping or anything.
Or adhesion. We don't add any glue or tape, so there's no resetting of the print bed at any point in time.
Yep. And just to add a little bit to that, that's been one of the things that we hate in the FDM world, is that people that were using hairspray and glues and everything else. We always tell them that is not the solution. The solution is either in better settings or better materials. You don't want that. It's just not good. So that's one of the reasons that I was really impressed right off the bat, because it had its resistance to residual thermal stress of these parts, and then when it cooled down, it completely released. And we actually did about I think maybe about 2 years ago, we did a case study where we actually took a variety of materials, everything from nylons to PETG, and we were trying to optimize which combination of build plate that was on the market was the right match. And at the time, in our studies, we could not find something that was catch-all. We could find that one type would do well with these two materials, one type did extremely well with nylon, one type did okay with polycarbonate, but this was our results. And our game plan was, okay, well, this will help technicians understand that when you're about to print, you're going to use this material, you need to go get this bed, slap it on there, and then go. If we're in your all's case, and they're testing, you're getting a material that is capable of handling them all, which is yet one more reason to make this a more automated and less human factored system, which you love. You can alternate materials. It's incredible.
One of the cool things we'll go into is what happens when materials don't work with the bed, because Steven's actually come up with a clever solution. So we can go into that later, or we will be going into that later. But I think it's kind of on this line of engineering materials, we should probably talk about nylon as well.
Yeah, so nylon is, in my opinion, even trickier to print than polycarbonate. You can see here we got nylon benchy. It printed out really nicely. It's using 0.5 millimeter layers, which I love. I love printing really thick. 0.8 nozzle, all those good fast printing settings as well. But nylon tends to warp quite a lot, and you'll even notice if you take a good look at the bottom of the benchy, there's a slight curve to it.
Let's see if I can pause it on there.
Yeah, it might not be super visible, but the point is that this nylon printed on an unenclosed Ender 3.
It was the sheer will of the print surface preventing it from warping.
Yeah. And so like what I found is when printing nylons, like there will be a small section right in the middle of the part that keeps stuck. And then yeah, the edges will peel off, and I'm sure having an enclosure would help with that. But like yeah, the first layer goes down great. Second layer goes down great on top of it. It's just like when there's 10 layers and they're all contracting at different rates, that's when the warping kind of sets in. So we're kind of looking at how to incorporate an enclosure with the Quinly. It hasn't really been like the top priority thing right now, because it'd be nice to be able to print these sort of things without an enclosure. But like nylon is probably like the case where we would want to look at using an enclosure. But that being said, you can get nice prints out of it, and you can see the benchy there looks quite good.
Eric, what's your experience
Yeah.
been with nylon?
Dehydrate it first. That's the
Oh,
first
yeah.
Absolutely. That's what this is for. We can fit more
yeah.
nylon spools in the dehydrator.
Actually, so the side thing, Mateo, you might want to just let people know this is a nice hack for a dehydrator.
Oh yeah.
So, Stephen, do you want to explain what this actually is?
Yeah. So if you have looked into nylon, you need to know that it needs to be dry. And the most common way that people dry their filament, other than putting it in the oven, is getting a food dehydrator, which are pretty cheap. I got mine for $40 Canadian on Amazon. And it's just basically like a towel, like a ring that heats up whatever's inside it to like a set temperature. So this is made out of polycarbonate just because of the heat resistance. And yeah, this essentially just extended the height of the filament dryer, so I could fit 2 spools of filament instead of just 1.
Yeah. So beyond dehydrate your filament, Eric, what else do you recommend to your students when you're printing nylon?
Okay, so I'm gonna throw in one more science thing to it too, because this falls into this whole category of like, well, look at you're having to take this material and you have to put it dehydrated, get it ready. Industry doesn't do that. Well, actually, industry does. If you're doing injection molding, the moisture control of your material is crucial. So I just want to align that with the realities of we're doing the same things that they do in industry with conventional manufacturing. It's just in a different form. So these granular pellets we're doing with rolls of filament. So it's the same material with the same pre-processes. So generally we will print our nylon on a case-by-case basis. One of our really enjoyable products that we love, we actually did for a company that actually is a huge manufacturer of food. So like your baked goods, your cookies and donuts that you get at which we're selling like mad cakes during COVID, but from the gas stations. They're actually produced by contract manufacturing companies. One in particular has about 26 sites worldwide, and they could not even keep up with the orders during COVID. One of the pieces of equipment that is used in the qualification process of the food it's making, the cookies, for example, is this big funnel. And we actually were using nylon, and it was actually the FDA compliant nylons, and with an open chamber system. But we really had to work hard on getting the adhesion down. So cranking up the bed was one part of it. The speed was a huge adjustment that we had to work with to deal with that bubbling effect. The shape also is something we use because the reason things warp is because of residual thermal stress. And you can think of it like this: you heat something up and all the molecules get all twisted and tighten together. And so as it cools, if it cools too quickly, those molecules don't get a chance to gently realign themselves. And so they're kind of like twisted like this. And so therefore they start pulling on each other, which creates the curling. So your heat control has a lot to do with that curling factor. And if you can do a chamber, or at the very least, if you can keep the printer system outside of like a continuously like an air conditioned environment, like if you have it right underneath a vent, that's not a good plan. But if you have it at a corner or located where there's not a lot of air blown across it, you'll actually get better results against that curling problem. You're right, the heat bed does do that. And of course, it's just shape too. If you can actually design your product that has a better shape to accommodate that residual thermal stress, if you avoid sharp corners, that helps a tremendous amount. It's like we would see on farmers. Sometimes they would go a fence this way and a fence this way, and the one on the end, the corner one, gets pulled in because you got forces going in both directions. If you round your designs off, you'll have less residual stress. And so that's a design solution that goes with it too. There are materials and adhesives people will try, but we tell them to work on that first layer of compression, get that first layer down super, super tight, crank up the heat, tell the first layer to go very, very slow, and then build up from there. And then try to keep it as warm and stable as you possibly can.
Yeah, definitely. Stephen had tried 2 different nylons. This was a Talman one, right?
Yeah, there's 910.
910. That's kind of the standard one, and then this was like a weird blend that's super flexible, right?
Yeah, it's called TPE. I think it's got a bit of TPE in there, which is thermoelastic something or other. It's this stuff, it bends. But mixed with nylon, so it's actually super strong and quite flexible at the same time. It's actually quite nice to print this stuff. It's like a semi-flex material, I think, but it's got super good toughness. Like if you guys know of like CNC Kitchen, this is probably the toughest material that the guy Stefan has tested.
Yeah.
And it printed really nicely. It stuck down quite well to the build plate. Again, there's a tiny bit of rounding off on the 2 sides there. But it's also important to keep in mind I didn't actually use a brim on these parts as well. You know, we kind of avoid brims in general just because of the amount of post-processing that you have to do when you wake up to like 100 parts. It's kind of daunting, so having the ability to print without a brim is actually super nice.
Yeah.
You know, in this case, I think I might go for a brim, but you know, now I know.
Yeah. Or an enclosed system.
Or an enclosed system, yeah.
Well, and it's an interesting transition part to our flexible materials, which is the next kind of group that you did. And I think I'm very excited to see
Yeah,
your
there's some interesting stuff there.
workaround. Yeah, you've got some
Oh, yeah.
interesting things.
Yeah. Flexibles have been like the number one question we get, whether the automation is compatible with. And kind of why don't you kind of introduce us to your work that you've been doing most recently with them?
Yeah, so the thing about flexibles is that they're really grabby. Like they tend to stick to things and they don't tend to let go. So that's the same thing with flexibles and the vapor build plates that we use. And so before I did all this testing, we were basically telling people, yeah, you can't really print TPU on these beds.
It doesn't come off.
Well, you have to peel it off. It doesn't get pushed off. It doesn't slide off nicely.
Especially because we were being asked to print really large surface area parts.
Yeah.
Yeah.
Yeah, and so, you know, having a large surface area connected to the build plate, you know, you'd ram the hot end into it and it would just keep on skipping and make angry printer noises and everything. It wasn't very good.
It's actually interesting because that's not an issue that's exclusive to our automation too. Like a lot of people use belt type printers and they actually work quite well for large TPU parts, but when you get into the realm of really thin TPU, they kind of go around with your belt and end up under your printer. Yeah. Like we've spoken to some people who do use it for production, and that's a pretty common issue. So your work these last couple of weeks has been trying to figure out how we can come up with a solution where TPU pieces, any size TPU part, can be printed and gain the benefit of the automation. So what are we looking at here? What did you do?
This is the new McCulloch method.
Yeah, there we go. It's got a name.
TPU printing. Eric, you can use that. It's a new brand.
Here, let's see if we can go. So this is the method I came up with is essentially just printing a raft out of PLA. You know, everyone knows what a raft is. It's like the first, you know, so something that you print the first few layers with so that it cancels out any unevenness on your build plate. And it also gives you a really nice smooth printing surface to start with. But the thing with PLA is that it releases really well from our build plates, unlike TPU. So what I've been doing, this is more of just a proof of concept. It's not an automated technique yet. but printing a raft in PLA. And then in my slicer, I set this just a pause at my first layer so I could change the material to TPU. And then it would just finish the rest of the print in TPU. And so you can see the part being released here.
It's not sticking.
It just released completely. Like it looks like I just put the part there, but trust me, it was printed in place like that.
Yeah, we're gonna have to get some more videos. But
Yeah.
something interesting, Eric, because before this stream we were talking about kind of alternative materials that you were looking at testing that we haven't done yet. And I think this McCulloch method might be the way to do something like that if you find things are sticking too much or not sticking at all.
Yeah, I think it could be a really cool workaround. And so you don't need to use just PLA. So for example, this one was printed on a PETG raft and it's not coming off.
Yeah.
Like I've tried everything, it doesn't come off. So it ends up being, the different material combinations might work really well. It's just trying them out.
Well, there might be applications where you want PETG with a TPU
And there you go. There might be
combo,
reasons to
and
do
it's
that instead.
perfect, and it
Yeah.
won't delaminate.
Yeah.
So, Eric, in terms of your experience, kind of teaching people how, first of all, do you work with like flexible materials often? Because I think from every trade show, that's one of the most common questions we
Yeah.
were getting was,
Yeah.
how well does it do flexibles?
Mhm.
Yeah. We do quite a bit in the biomedical side of the operations. There's a couple products that we are testing now for stroke victims that we designed and customized for folks, and it's TPU based. And it's part of the muscle rehab process. And of course, in that scenario, we're just printing on open, and we're using build plates that we know just adhere to TPU and let it go. Generally, if we have adhesion issues, we will solve it on the design side before we'll engage in, if we can avoid any kind of adhesive or any kind of extra component to the automation, we'll do it that way. And again, we look at design whenever possible for that. So we might turn around and add an extra base layer. Another thing that we saw too is one of our other guys, he does a lot of special grips and crafts for certain applications. And he was doing a lot of TPU work. He's actually got it really dialed into thin objects. And he was using an enclosed system and had a lot of good results with that too. But yeah, our first go-to move is generally see if we can design a better adhesion as part of the design overall of the product, or something that we can actually automatically remove after it's done, even to the point of saying, okay, we'll turn around and do a really dense structure to adhere to the bed, and then we will create a very spiky kind of thing and then start our actual object. So we'll maybe make a custom raft that's designed to translate that. Biggest problem with TPU that we see is as it gets taller and thinner, that wobble, your actual friction just associated with your extruder pulling that bead along can shift it out of whack. So you can get a little stuff there. We do try to do pretty good compression on it, depending on what kind of driver system we're using to push it down. But we actually have probably a pretty high success rate with TPU. But we're also not trying to do any kind of crazy shapes either. We're usually doing things that are cylindrical or grip-like in their nature.
That support method you're talking about with the spikes that allow it to come off easily reminds me of kind of what those companies like Desktop Metal were doing with the ceramic first layer that kind of has very small, it's got a good ceramic base and then very small contact points before the actual metal part. Kind of reminds me of that method where you're just using a dense but like low kind of contact area to remove the parts.
Yeah, there's software is beginning to really understand additive, and you're seeing a lot of software companies come up with really innovative solutions. So actually earlier today, I was on the phone with Autodesk, and we were talking about this concept of low-cost additive and how we can optimize these banks of 3D printer farms to allow small businesses to start up. And so features like that, features of taking your design model, here's what I need, and then using artificial intelligence and other systems to look at the surface that I'm going to print from and say, okay, this is going to be the perfect raft support system, whatever the case may be, that is easily removable, but I'm going to get maximum adhesion when heated. And so our software is really going to allow us to optimize what additive's capable of to go with these materials, basically design solutions for different material types.
Absolutely.
Yeah.
And the reason we got started on TPU is that, as Mateo says, we get questions all the time at these trade shows, and particularly with respect to insoles.
Yeah.
Yep.
But of course, if you're going to do a PLA raft, then the post-processing question comes in, Stephen. So
Yeah.
Oh yeah.
interested to hear about. So two things we do know about insoles: TPU is not okay against skin. You have to so with the insoles, our understanding is that anybody who's printing insoles with TPU has to apply a cloth cover to go between the skin and the TPU. So you are handling the insoles anyway, but how hard is it to get the raft off? That would be, I think, the person's next question, right?
Oh, good thing you asked.
Oh, it's almost like
Here's one I prepared earlier. So we got a TPU insole attached to the PLA raft. I did this this afternoon. So why don't we just see how easily it releases?
Eric, can you see this? Because the camera's sort of a
This
way
is
back.
yeah.
On some of that. I'm just having to use my mind to visualize.
Okay.
All right. Well, put it close to the microphone so you can hear it peel off. Here you go.
You can watch the live stream afterward.
Yeah. Let's go.
That's right.
So
So let's see how hard it is to take it off. Holy smokes. That's it.
quite nice.
That is a clean
Not too
peel.
It sounds pretty cool as well.
So at least, as you know, given this is early stage technology, this is not bad. That was, how long did that take? A second and a half.
About a second. Probably put it down to 0.8.
Probably good. And the interesting thing is, if you look at the resulting pieces, they're pretty clean. And we haven't even dialed this in yet. Like,
Yeah.
this is brand new. You guys are watching leading edge, brand new research. So
And you're going to be standing on these. It's not like you're going to be feeling,
Yeah.
a 0.2 millimeter layer. You've got a cover of cloth stock underneath there.
exactly.
I think to Eric's point, part of why this is really cool that Stephen came up with a way to support these materials that wouldn't work directly on the bed. We were having a conversation yesterday with Carrie from Fabaloo, and we started talking about something you had mentioned, which is like how 3D printing is becoming more and more software driven. And what's really exciting about this material testing to me and the prospects of this is that kind of alluding to what you were saying before, where typically if you wanted to print a different material, you would have a specific bed type for that material. What I find really exciting, and I can see a whole bunch of possibilities with the automation, is that with the vapor bed, your hardware stays constant, and you can switch materials. And now you're completely controlling your production process through software. And in our case, it's either a matter of having 2 extruders that you can just print and generate a raft for parts that require it, or just print at a different temperature where the plastic sticks and releases to the bed. So I find that super exciting, because something that I think a lot of print farm operators start to run into as they support not only more materials but more colors is like you have to build your hardware to specific applications. And part of making Quinly being kind of pretty much agnostic to at least the materials we're going through today opens up a lot of doors in terms of like being able to offer pretty much low cost automation and not having to deal with keeping track of what printers can print what objects. So
your flexibility that you're providing, again, it goes back to why additive is so different. Again, compared to injection molding, you can make, your options are whatever color you choose. That's your limit. But a printer can switch materials, it can switch design, and it can switch it that day without any retooling. So what you're describing and getting that dialed in even more is absolutely what we need in this technology to become to the forefront is that flexibility, that pivot. I don't know, there's a lot of great small businesses that are producing, 100, 200 different products off the same print farm, and that's just crazy.
There was an Etsy store we had interviewed a couple weeks ago where it was I think it was one guy and his wife running it.
Yep.
And their product page, they had over 200 unique products listed, and then those products would be made up of smaller pieces. Yeah. So just to answer, there are a bunch of questions in chat. So the PLA raft and the TPU print test was actually done on the Ender 3. All of the prints we're talking about today were done on Ender 3s.
Unenclosed.
Unenclosed, yeah.
Yeah. So we could get better quality for sure if we had enclosure on this, but we want to see what the raw Ender 3 can do.
Yeah.
Yeah, and just to answer the question about the dual extrusion, it was in this case it was simply just pausing at the first layer of the TPU print, changing the material manually, and then clicking to resume the print. But you can imagine how this would be done with a dual extrusion setup.
Yeah, absolutely.
Combine filaments together. I mean, your ability to like filament in on top of filament,
like with an MMU or a pallet, like that kind of thing.
Yep.
There's a lot of options coming up on the market for this type of thing.
Yeah. So like pretty much it could be fully automated as long as you're running a dual extrusion setup. We pretty much need to get one in, and then we could prove it out by running it 24/7 for a couple of days.
Yeah. Just Quinly takes a lot of effort right now, but we're certainly looking to this as something to look into.
Yeah, especially if we find some like really compelling use cases, like the insoles, for example.
Yeah, pretty good use case.
Yeah.
Yeah.
So why don't we quickly
move on
from flexibles, because I think we've given them a lot of love. One of the really cool things, just to close it out, was you also did polypropylene, which had this crazy material property. I don't know if I would say it's like production ready yet, at least on an unenclosed printer, but I'll have to send these pictures to you, Eric, because you'll find this fascinating. So you were printing, from what I understand, you were printing polypropylene parts, and they stuck really well when the vapor bed was hot. But they stuck so well that, and polypropylene is like a really soft material. You described it as if you were printing with hot glue.
Yeah.
And what you can see, or what they can see in these images is, when he printed these objects, the first layer stayed stuck to the bed, and the warping force of the rest of the layers, and polypropylene's notorious for warping, actually pulled the layers apart.
Yeah.
Like outside of the print, so the adhesion force between the bed and the first layer was actually higher than the interlayer adhesion of the kind of soft, warm polypropylene, and we got these really weird results with it.
It was really cool to actually see this happen. The bottom surface is all bubbly and everything because I guess just air finds its way inside as the layers tear themselves apart.
It's kind of like opening up a grilled cheese sandwich.
Yeah, that's actually a really good way to describe it. Yeah. But yeah, it's cool how the first layer remained really, really well stuck down. And polypropylene is notoriously hard to print with just because it doesn't stick to very much. So everyone prints it on polypropylene tape.
Yeah.
But in this case, it seemed to work really well. It's just the warping forces were crazy on this. And I think it being a very soft material doesn't help.
Yeah.
So an enclosure would be almost mandatory for this kind of thing, I'm pretty sure. But it was just really cool to see how we might be able to print this if we had an enclosed system.
Okay, let's go on to more standard materials.
Okay, cool.
So next up we've got PETG and HIPs, and also copolymers. So these are kind of, I find these materials quite interesting. PETG is pretty popular everywhere nowadays, but copolymers don't seem to be super popular over here in North America, at least from my experience.
Yeah.
I'd be curious to hear from you, Eric, if maybe you have a different opinion, but they seem to be very popular in Europe. Like I know ColorFab stocks a whole bunch of different blends. Yeah, like where do you see these types of materials being used, at least in your experience or in industry?
So we don't see, I mean, you've got ABS as a copolymer, you know, so you see it used a whole lot in industry in general. The additive side of things is, or at least from our angle is, we're going to try to do something that is either not done or is like a huge transition. So we have a tendency to focus a little bit more on the things that you can't injection mold with. So for example, carbon fibers and, you know, your graphenes and those kind of things, which have some great stuff. Now, you know, your copolymers are used in injection molding all the time. And of course, we all know what the major problem with ABS is, and it's that residual thermal stress factor that just makes them warp off. So I can't really speak to a whole lot of that because we have a tendency to focus on the stuff that's more exotic than the stuff that's mainstream.
Yeah.
Now you can look at some of your vinyl acetates and those kind of things, but we haven't played around with them too awful much.
Yeah, I mean that makes sense. I think they are out there, like from what I've seen too. They're kind of out there, but people definitely love like nylons, polycarbonates, and then obviously all those composite materials. I did notice there was a trend recently though to put composite in PETG. I think we have a sample of like carbon fiber PETG, and I'm curious kind of where that application comes from as opposed to putting it in something like nylon or just straight up PLA. It's a bit easier to print those.
People are just trying stuff and just to see what hits, man. I think
Yeah, what sticks.
Yeah.
make everything together and see what happens. We're doing that in our lab. I mean, we're mixing all kinds of stuff together into our filament makers to see what happens. But you have some advantages there. I mean, that's how we have all the materials that we have anyway, is you start mixing things together and finding out if there's a new property that we never anticipated. PETG is great. And we printed out a tremendous amount of the face shields out of the PETG side of things. It's stronger. It has the heat resistance the PLA doesn't have. It typically has just a little bit more flexibility. It can have a really, really nice look to it if you actually really compress those layers. So adding in a stiffening agent, like a carbon fiber component to it to increase resistance, or maybe even make it more of a hard material, maybe increase its tensile strength just a little bit, it just gives it that extra bump. And I think you'll see a lot more of that. Right now, the real interest is all of these organics. And we're trying to throw hemp into PLA. We're trying to throw, basically bringing me, like I said, a bunch of hops to actually build into a new type of filament. So I think it's just the fact that, hey, we got this material, and much like the rest of the plastics industry, we're turning it into a new process to say it's got some kind of little attribute that's a little bit different than everything else, and let's see what it does.
Cool. Yeah, I think kind of, there are a lot of, just on the material side alone, there's like a lot of these kind of emergent properties that you get when you're making these composites, but yeah, I think we've tested PETG, we've tested what ColorFab brands as copolymer, even though copolymer is about as narrow as thermoplastic in terms of a category. And we've also been printing with hips, and I've just got one last clip in terms of our material run through here, which is a test that Dominic did at home late one night.
Last night.
Last night. Where he learned about how the hips can actually work with the printer, but also he learned about the importance of having a proper material collection bin. So if you're just listening, he's got like a recycling bin in front of his modified printer, and he's printed this carabiner. and the nozzle slides it off. It shoots straight past the bin onto the ground in his kitchen.
Yeah, so make sure your part catching bins are in the right place.
Yeah,
Yeah.
that's lessons learned.
Although we know from experience that these plastic parts can drop long distances,
Yeah.
fly long distances, and
Oh
be
yeah.
Yeah.
pretty uninjured.
Yeah, I think shelves were like the last thing we did.
Yeah,
That
shelves
we
were-
put the Q pods in.
So, Erica, you haven't really seen our Q pods, but they're about 7 feet high, and we didn't have any shelving when we were doing R&D for the first 6 months. So parts would just drop off the top printers straight to the floor, and they were fine.
Yeah.
It's perfectly fine. So just the last thing we'd like to go over, Eric, we just want to show people your donut. We're so impressed with your donut.
Well, you can pull that. I'm assuming you'll pull that up on the screen for me.
Yeah,
Yeah,
I've got a bunch of pictures on the screen here.
All right. So again, we always go back to the concept. It's about design, and polycarbonate, ABS, nylon. Here's the problem with FDM printing. It's your Z-axis weakness. No matter how great of material you have, its weak plane is going to be the layer-to-layer adhesion. So the solving of the material doesn't necessarily solve that problem. What does solve that problem, though, is how you design. And so what you're seeing on the screen is the donut that we actually use it for the Additive Guru channel on YouTube. We'll plug for that. You can check us out, and we actually put out a lot of material for people to learn how to 3D print and advanced tech. But here's the deal, that donut, because people used to come in my lab, especially industry guys, they would come in my lab and want to grab a hold of my parts and break them. They just love to break my 3D printed parts. So I was like, well, the heck with that. And so we started printing these donuts off. And you'll notice it's a lattice structure. And thanks goes to Entopology for allowing us access to their software that generates this lattice structure. And what's great is I can put these donuts in these guys' hands, big old dudes, they get all red-faced trying to break it. They can't even touch it. I mean, it's going to take roughly 400 pounds of force to break this donut. And then I tell them that thing is printed on a $200 printer with dirt cheap plastic. And it gets their attention when they realize that the power of this technology is the ability to control the shape. Even a lattice structure where I can mimic the atomic structure of a carbon atom. That's the power here. And what we've also noticed too is in the more exotic designs, lattice structure and also using generative, like with Fusion 360, we are able to control or address the Z-axis weakness through shape change. And we can take a PLA part. Yeah, it may not do that great in heat, but I can make the part still super strong to the forces that you plan on applying to it. So that is probably the biggest part of the story in all of this. And so right now, back in the lab, our new system, our new kit is just knocking off donut after donut so I can spread that word. And we'll move up. Our next project after the donuts is that we'll move up to doing some of our more advanced generative designs. And these parts are crazy. They look like they were grown, not manufactured. They look like bone structures. They look like something that was grown out of a pot, and yet it's a solid object that has incredible resistance in terms of stiffness and strength, and yet it's still made out of PLA. But it's the design that makes a change. Even the inconsistencies that it will design into the product, like almost like a porous, not porous, but maybe like a rolling hill kind of thing, that changes the stress distribution of the part, and you can just feel the strength in these parts, and yet it's the same stuff of the keychains and trinkets that we're seeing broken all the time. So the donut is the way that I get that thought process going, and we make them by the bucket loads when we're not making face shields in COVID. So we want, actually folks can go to our webpage anytime and download that file and print it off for themselves and just get that concept out there. But yeah, that's the donut, the Additive Guru donut.
Yeah. Or the torture donut, as we refer to it internally.
Yeah.
So, and there's tricks to understanding that too, because this lattice structure, you're starting off with like basic pillars. So sometimes we'll lower it into the bed just a little bit more on the slicer side, so it gets a better starting layer. But yeah, you'll find when you print these type of things off, for folks that do that, they can actually just feel the strength.
Mm-hmm.
And yet it doesn't matter what material you're producing this in, you're going to get a better product when the design is more complex and you're using this kind of next generation design mentality.
Yeah. Jeff's got a couple questions for us. He's been asking about the size of the print beds. We do have a couple being fabricated in different printer sizes for testing. So we should be able to, I think we should be getting them in, or they should be done being made in a couple weeks. So it is definitely something we're really, really interested in exploring, especially larger printers. Yeah, so hopefully that
But
answers your question.
we have done some force tests. If you want to see what sort of the adhesive force is, we've got videos up on YouTube. And just take a look at the force test. You'll get some sense of what we've kind of seen that might be some of our capabilities.
Yeah.
Yeah, just out of curiosity, when you do your force test, do you do it more in shear or do you do it like in vertical pull?
It's a great question. I think we've been doing a bit of both, because shear is most important when we're removing parts from the build plate, because that's just the way that we knock them off. But like it's easier in general just to test things in tension because you can just pull it straight off. But in general, I think shear is more important for our purposes, because we need it to be able to slide off easily once it's cool. And also when printers are moving back and forth, it's not pulling upwards on the print. It's, creating a bit of friction, dragging back and forth. And if the nozzle catches on something, it could push it sideways. But yeah, so shear is probably more important to us.
But in our industrial system, we actually print on 90-degree plates instead of what you have on the Quinly, Eric. And so, that's the other thing that we have to look at when we're doing. Oh, there we've got a video of them doing it on the Quinly. But what is that? That one's about 4.5 kilo. But we've been up to 6, 7.
I think 6.5.
6.5.
Across. This is a 3 by 3 centimeter area. I know Calvin calculated with the.
It was like 8 psi or something
Yeah.
like that.
So this is just a little piece of literally a Post-it note, and
That's after it releases.
this is when the print is done and it's cool. But
0 psi mode.
Yeah, exactly. We just, because people kept saying to us, sending us notes, oh, you're just jamming it off the bed, but we wanted to show we're not jamming it. So there you go.
It'd be great to post that, like to throw that into an Excel or something or a database and just post that out even as a PDF, because that's good data. That's good data in terms of adhesive strength to share and for folks to really get a feel for. So I'd put that out there for full tests.
Yeah, we'd love to do it in a more rigorous way and try and find out what the limits are. So if you've got some students looking for projects, Eric,
Yes, that's the catch. And there's one thing that we'll point out too is that one of the things that we're really interested in our lab is that next generation application, specifically your ability to print metals, infused metals on desktop printers. So that's one of the things that we'll be looking toward testing with your all system is, can I start printing stainless steel on this and turn it into a production model, which I'm very excited about the potential to do that. I think that would be just tremendous opportunity for an automated metal production system, because that just flat does not exist. CNC basically cuts a part. Somebody has to be there, put that part in there. But if I'm turning around and actually knocking off metal parts off an automated printer, that's going to be wild.
that's 2021.
Yeah. Yeah, the prospect of that would be pretty incredible. And maybe, yeah, exactly. Maybe to hit Jeff's question with that, and if it doesn't work, we can always look into doing the raft method, where we print with a material that does work.
Yeah.
And just print on top of that, like with TPU and the TPUs we've been doing.
Yeah. Well, I think we're a little past time even, but thank you, Eric. We really appreciate you joining us. Every time we talk to you, we have such a great conversation, and we're interested to see what kind of stress you put the system through. So I'm sure we'll be getting some more photos and stuff. And
Setting it up for some good data and demonstration. We generally like to provide case studies, and everyone's welcome to come see the materials that we have already
Out there, especially if you're interested in convincing folks what additive really is. You can actually find my webpage pretty easily. You can just type out SCC 3D printing, and it'll probably take you right to our page. We'll be right underneath the ads. Or yeah, that's where we'll be. Or Eric Wooldridge. You can type out Eric Wooldridge in Kentucky, and any combination of 3D printing, you'll find me that way too.
yeah, that's true. You come up top of the page.
Yeah.
It's that unique name at the very end that helps.
And then, of course, there's your
but we
YouTube
do-
channel as well.
The Additive
That's
Guru.
right. Print those donuts. That's where the donuts are off our page. At the bottom of the screen, you'll see like a little link, and you can actually go download some STLs and those kind of things. But we appreciate the opportunity to partner with you all in this test, because you're right where we want to be, and that's automation, and that this basically helps us eliminate one more problem in the supply chain.
Yeah. Well, thank you so much for joining us, Eric. And Stephen, thanks for doing all this material testing over the last bit. I know it's been intense, and we've got some great parts and great results. I know you're going to keep on working on stuff. So
Well,
I
there's more
expect
materials out there that I haven't tested.
just a few, according to Eric.
Just a few.
He might have a dozen or so for you.
Some materials that are more metal than plastic.
Yeah. We're looking forward to that shipment.
Yeah.
And for those of you who are interested in Quinly, of course, 3dq.com. These broadcasts do go up on twitch.tv/3dq, but they also are on our YouTube channel. And if you just Google YouTube 3dque, you'll pretty much find us. And we're always excited to get questions from people on our Discord community channel. So certainly invite people to join us there. And Mateo, do you want to say anything about next week? Some of our models and props. Maybe we can bring up Honey Badger's. Having a special guest next week from the UK, Honey Badger Print and Paint. They do very cool props models, cosplay type of work, and they use a lot of FDM printers, and they paint most of their stuff.
Yeah, that's going to be interesting.
It's going to be really interesting to talk to them about that. They do use a variety of different printers, and they are also one of our reviewers. They're testing our kit. They're super excited because they have other jobs and don't like standing around waiting for prints and waiting to scrape off prints. And
something all the reviewers have in common, it seems.
Yeah, it's the sleep thing. I don't want to get up at 3 o'clock in the morning.
That's right.
So certainly invite everybody back next week.
Yeah.
For that. And
just thank you again to Eric. I'm really looking forward to the type of testing that you end up doing with the kit. Yeah, and of course implementing all the feedback we've gotten so far from you guys.
Yeah, it's great. Yeah.
Definitely kudos goes out to Justin. He is great at troubleshooting, and he will take care of you in that respect. He'll figure out every bug for you.
Yeah. Yeah, we had a fun troubleshooting call the other week.
Yeah, Justin's been amazing. So
absolutely.
So thank you guys for all your support, and hopefully we'll see you on other live streams.
Yeah, absolutely.
Looking forward to it. We'll have some good data for you. So you all have a good night, and thank you very much.
Thank you.
You too.
Bye-bye.
We're back.
We're back.
We're-
I didn't realize we had Danica on. I didn't see her on the screen. So Danica, where are you? Let's see.
Let's pull her up.
Let's pull her up.
Oh
and
wait, that's
see.
Media Man.
That's me, man. Whoops.
We don't have video, but we do have.
Do we have audio? Maybe.
We might
Maybe
have
not.
audio. We'll see if she's here. Oh, apparently we do. Hold on.
Screen. So
Hello?
Danica, where are you? Let's
Uh-oh, they've got
Let's
the
pull her
stream
up.
open.
Let's pull her up.
Do you mind closing this, muting the stream, please?
It might not be
We have
clear.
Maybe.
We might
maybe
have
not.
audio. We'll see if she's here.
We're here.
Hold on.
Screen. So
Hello?
Danica, where are you? Let's
Uh-oh,
see.
they've got.
Maybe we'll do it next week.
I think in light of the technical issues, we'll do it next week.
Yeah.
Danica is our newest tester, and we're really excited to show kind of what the type of work she'll be doing in 3DQ. She's going to be featuring in a special video. Yeah, she's going to be testing one of our systems, so I'm really excited. I think next week we'll have her on right at the beginning and
Yes.
and ask her kind of how she got into 3D printing and all of that cool stuff, and see how she likes using the printers.
Yeah, be cool to get a different perspective.
Yeah, absolutely. So that's gonna be a super surprise. If you guys have any more questions, definitely ping us in the Discord. Again, it's just under the channel. We'll all be around to answer them. But I think for today, that's
it.
That's
I think
it.
That's it for today.
all right.
Cool.
We'll see you next
Thanks,
Wednesday.
everybody.
Bye, guys.
Any
You're
more
a surprise.
questions?
Nobody
Definitely
knows that you're
ping
only
us in the
8.
Discord. Again, it's just under the channel.